Hi. Today's video basically you're wondering what is it all about. Well, today's video it's basically based on and it's all about a school project. A lot of parents they come to me and they said, you know what, my child has to make a project for the educational department or for competition or whatever. Please help. We can't get components, we can't sort of put it together, we don't have a soldering iron, we don't know what the transistor is, we don't know how to approach the sort of thing. So nonetheless, one of the projects that we basically make, we make a full project, like a complete, or in a kit form, complete sort of unit, or we sell it, we sell them as basically components, and then customer puts it together. And today's topic is basically all about a project called Fire Alarm. Now, the children they have to demonstrate to the education department, and that is, in case there is a fire, some means of detection and alerting the person. Obviously, this is a miniature sort of circuit that are quickly slammed together, and I'm basically selling it as a complete project, complete sort of made-up project on the cardboard. The only one thing is, customer buys the battery, PP3 battery, fits it over here with a double-sided tape, and basically this is what it looks like. Or we sell the components and customer must put it together himself. So what is it all about? How does it work? Oh, well, I will demonstrate it just now. Now, let me do the demo and then I'll do the explanation of components, what it involves and how to operate. To demonstrate it, I've got a little candle over here. So what I'm going to do is basically I'm going to light the candle. Okay, I'm going to light the candle with the lighter. Okay, now the unit is already on. Okay, the unit is already on. Okay, here is the sensor. And now you're wondering, why did I put actually... Okay, let me put the candle to the side. Why did I cover it? The sensor is here. And it's called a phototransistor that I have used. Of course, one could use a infra red diode, receiving diode. But I've chosen a phototransistor because the spectral wavelength of this particular phototransistor is from about 400 nanometers to about 1400 nanometers, and that is basically the spectral wavelength of the infrared sort of heat generated by any flame or any fire. So that's why I specifically use this particular one. But now, obviously, all the surroundings, and I got the fluorescent lights on top of me, etc., and so on, soldering irons behind me, instruments to that side over there, and so on. Solder station is on the right hand side. All that generates and emits the heat. So in order to be able to pinpoint more or less the area, what I have done, and it's advisable to narrow the actual beam. So now only sort of certain area that you want to control, you'll be able to sort of trigger. It will be able to trigger the actual alarm. All right, so now let me show you again. Here is the candle, small candle, I lit it, and watch what happens with the LED, and the audible DC buzzer will come on once it detects the fire. You can see it. Right now, the flame is emitting the infrared magnetic wave, invisible magnetic wave, obvious, which is actually infrared, and it's anywhere in that range between, okay, let me just cut it off, anywhere in the range between 400 to 1450 nanometers. That is the wavelength of the of the actual receiving transistor. So now one more time, and it's quite sensitive. Now I'm approximately about 30 centimeter. Let me just sort of shift it. Right now I'm more than nearly a meter away. Okay, I can't operate the camera, but it's approximately about a meter. Let me just look at it where the candle is. Look at it where the candle is. Candle is right there. And you can actually see it. Okay, so let me bring it back again. Okay, the closer it gets, the louder and the brighter the light sort of will shine. Okay, so because it's a stronger infrared transistor, phototransistor will conduct more, it will bias the actual transistor on the base, and it will switch the transistor harder, and it will let more voltage go into the buzzer and the LED. So the brightness will become bigger, and the sound will become louder. Now, one more interesting sort of fact, let me show you. While we talking infrared and the light, invisible electromagnetic waves, okay. Now you can see I just shifted it about 30 degrees that side, top or 10, and I'm missing now the fire. Now you must have heard that the black color absorbs the actual heat, infrared and things like that. Yet the white or shiny or silver, it actually reflects the infrared light or radio waves for that matter, two-way radios or any signals and things like that. And you must have seen on YouTube where the people, they say, they put the reflectors behind the routers and things like that. Do they work? Yes, they do. Just you have to find the right angle. Now, I'm going to demonstrate. I'm going to use this sort of metal plate, silver, or let me start with the paper. Let me start with the paper. Okay, white reflects. Although right now it's not facing the fire, I'm going to put the paper over here and watch what happens. Can you see? Right now the signal is bouncing. Let me do this so you can actually see it, what I'm actually doing. Okay, now I remove it. Look at it there. Okay, let me explain. Put it down. Right now the infrared gets bounced off the white paper, and white reflects, sends the sort of received at the point of incident. That's a point of outward signal, or let me just switch it off. In other words, it will reflect the infrared from the paper, and it will sort of reach the phototransistor, which is covered inside. Okay, right now it increases the angle. Okay, all right, so what I'm trying to say is, so with this we actually demonstrate that the white color definitely does emit. Okay, and then let's take silver for argument's sake. Same angle, same everything. Okay, let me just do this. Sorry, let me, okay, this one is dirty, quite a, okay. Okay, you can see it. Okay, just a different reflective, so I had to change slightly the angle for argument's sake. Okay, but it still picks up the infrared, bounces off here, gets picked up by the actual phototransistor. Okay, now let's try it with the white one. Okay, same angle basically, picks up infrared, reflects it, gets picked up. Now let's try the black color at the same angle. Okay, I've got a black pouch, whatever, leather, and it's a definite black color. Let me try and put it. Same angle. Okay, you can see over here. nothing happening. Okay, absolutely nothing. You can see it. Now let me try and put the paper on the front, and then you'll see how it's going to actually reflect the signal. Can you see? White reflects, black absorbs. It does not reflect any radio waves or infrared waves or signals and things like that. So that is another sort of aspect of this little that the teachers could actually demonstrate. Let me just shift it so it doesn't make a noise, or I'll just switch it off. Okay, I switched it off. Another sort of thing that teachers could demonstrate for the children and grown-ups also. That what the physics teaches us, yes, it does work in practice. So if you want to improve the signal in the long and the short story, just to add, you can play around with a reflective aluminum or any sort of shiny metal type of thing in order to be able to concentrate and focus and redirect the actual magnetic wave, radiomagnetic waves, besides the infrared and things like that. Yeah, on that note, I hope I explained it well. Now, just coming to the nitty-gritty over here, how it operates. Basically, it consists out of the sensor, which is actually a phototransistor, okay, spectral length 400 to like 1500 nanometers, call it, okay, limits the current with the resistor, okay. Then we got basically we got a transistor over here. So the phototransistor is connected to the base. Okay, let me just focus over here. It's basically connected to the base of this transistor here. Okay, and once it detects the actual signal, which is the infrared, it will start conducting, and it will and make the base positive. And that's an NPN transistor. So once the NPN transistor gets a positive positive signal with respect to the emitter, it actually switches on, and then the collector starts conducting positive voltage through the diode and through the actual buzzer, which are connected to the actual collector of the transistor. And then inside, because now transistor is conducting, it's actually acting as a switch, makes a sort of low impedance down to the emitter, which is connected to negative. So the circuit is closed, and the voltage basically from the battery is basically applied now, and it flows through the LED and the actual buzzer. So that's basically sort of the principle of the fire alarm. Of course, you do get the sophisticated ones that are capable of much greater distances and smaller fires, or dedicated sort of fire detectors and things like that for specific sort of liquids. Specific depends on the sensors and depends on the sensitivity that you and how many sort of preamplifier or amplified stages you have. Of course, you can connect it up with your Arduino to send you the signal via the say Wi-Fi to your cell phone and things like that. So, but in a nutshell, that's not the scope of this particular video. Is just this little fire alarm that we started making for school projects. I hope I explained it well, and it's a nice little project, and it has got a practical sort of application, and we sell them as a components, so you can build it yourself, or we sell it completely sort of built. It's reasonably priced, and yes, it does work. So just maybe you're interested to see it one more time. Let me do it one more time. I'm just going to light it up. Nothing happening. Watch now. Picks up, and up to 1 meter, which is quite good. A block, no infrared reaching the actual sensor. There we go. And remember the black and white story. Black absorbs, white reflects. And on that note, I say thank you for watching Batos Fire Alarm.